In this video, we're going to discuss using the conjugate beam method to compute slopes and deflections in beams. So the basis of the conjugate beam method comes from the similarity in between or the similarity among several relationships. So for example, we've established before that the first derivative of the shear force function gives us the intensity of the load. We've also established that the first derivative of the rotation with respect to x is equal to m over EI. So the similarity between these two relationships is what forms the basis of the conjugate beam method. Similarly, we established that the second derivative of the moment with respect to x is equal to the value of the distributed load, and the second derivative of the displacement with respect to x is equal to m over EI. Right? So we see similarity between these two relationships and between these two relationships. Now, if we integrate these sets of relationships, we get that. So for example, if we integrate this relationship, we get that the shear is equal to the integral of the distributed load. And if we integrate this one, we get that the rotation is equal to the integral of the m over EI diagram with respect to dx. Similarly, if we integrate this relationship twice, we get that the moment is equal to the double integral of the distributed load with respect to x, and the transverse displacement is the double integral of the m over EI function with respect to x. So what we see here is that the shear compares with the moment, and the shear compares with the slope, and the moment compares with the displacement. And then we also see that the load, the distributed load, compares with the m over EI diagram. Okay, so now we're going to make use of these comparisons to do the conjugate beam analysis. So let's consider a beam that has length L, and it has an arbitrary distributed load. And we'll call this the real beam. And then we'll consider a second beam that has the same length as the real beam, but it's loaded with the m over EI diagram of the real beam. The supports of the conjugate beam we'll talk about in a sec. So again, the conjugate beam has the same length as the real beam, and it's loaded with the m over EI diagram of the real beam. And we will talk about how we get the supports in the conjugate beam in a second. Now, based on the relationships that we established earlier, we get two theorems. The first says that the slope at any point in the real beam is equal to the shear corresponding to the conjugate beam, right? So if you can compute the shear at a point in a conjugate beam, that would correspond to the slope in the real beam. The second theorem says that the displacement at a point in the real beam is equal to the moment at the corresponding point in the conjugate beam. In terms of the supports of the conjugate beam, the shear and moment at the supports in the conjugate beam must correspond to the slope and displacement at the supports in the real beam. And we'll see how that plays out in terms of how the supports compare in the real and conjugate beam in a sec. Something to keep in mind that if we neglect axial loads, a statically determinate real beam will also have a statically determinate conjugate beam. Okay, so going back to the relationship between the supports in the real beam and the conjugate beam, we said that the shear and moment at the supports in the conjugate must be equal to the slope and displacement at the support in the real beam. So let's look at some examples of the relationship between the supports in real and conjugate beams. So for example, if your real beam has a pin support, that means it has a non-zero rotation, but the vertical displacement is going to be 0. So that means that your conjugate beam is going to have a non-zero shear, and the moment is going to be 0. So that also corresponds to pin support. In the case where you have a roller support, your real beam, there's a rotation at that support and there's no vertical displacement. So again, for your conjugate beam, you're going to have shear at that support and no moment, which corresponds to a roller support. If we take the case of a real beam that has a fixed support, that means that the rotation at that support is 0, and the displacement, the vertical displacement, will also be 0. So that means that in your conjugate beam, the shear would have to be 0 and the moment would have to be 0. So that corresponds to a free end. And then lastly, if we consider a free end in your real beam, that means that there's a non-zero rotation and a non-zero transverse displacement. So that means that you have to have a non-zero shear and a non-zero moment, which corresponds to a fixed support. In the next video, we're going to implement the conjugate beam in an example to compute the slope and displacement in a beam.